In this video, we will discuss differentiation of exponential functions. Given that you're taking calculus this semester, I'm assuming that you've previously studied exponential and logarithmic functions. So I'm skipping the first 3 sections of this chapter because I can't be certain you've studied this stuff before. I'm posting links below to my Tech Math 2 reviews of exponential and logarithmic equations, both slides and videos. Please review these if you need to and contact me with any questions. The derivative of the exponential function. The derivative of e to the x is equal to e to the x. Using the limit definition of the derivative, we see that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h, which is equal to, in this case, the limit as h approaches 0 of e to the x plus h minus e to the x over h, which is equal to the limit as h approaches 0 of e to the x times e to the h minus 1, which is equal to e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Further, the limit as h approaches 0 of e to the h minus 1 over h is equal to 1, which we can see by taking values of h close to 0 and evaluating the value of the limit. Using this result, it is clear that for f of x equals e to the x, f prime of x equals e to the x. Find the derivative of each of the functions below. F of x equals x squared times e to the x. We use the product rule. F prime of x equals x squared times the derivative of e to the x plus e to the x times the derivative of x squared, which is x squared times e to the x plus e to the x times 2x. So that's x e to the x times x plus 2. G of t equals e to the t plus 2 to the 3/2 power. We use the general power rule. So g prime of t is equal to 3/2 times e to the t plus 2 to the 1/2 power times the derivative of e to the t plus 2. So then that's 3/2 e to the t plus 2 to the 1/2 power times e to the t. So we get 3/2 e to the t times e to the t plus 2 to the 1/2 power. To enlarge the class of exponential functions to be differentiated, we appeal to the chain rule to obtain the following rule for differentiating functions of the form h of x equals e to the f of x. The chain rule for exponential functions. If f of x is a differentiable function, then the derivative of e to the f of x is equal to e to the f of x times the f prime of x. Find the derivative of f of x equals e to the 2x. F prime of x equals e to the 2x times the derivative of 2x, which is equal to e to the 2x times 2, which is 2e to the 2x. Differentiate the function g of t equals e to the 2t squared plus t. G prime of t is equal to e to the 2 times 2t squared plus t times the derivative of 2t squared plus t, which is e to the 2t squared plus t times 4t plus 1, which is equal to 4t plus 1 times e to the 2t squared plus t. I'm only changing that around because it's traditional to put that polynomial before the exponential term. Differentiate the function y equals x e to the negative 2x. We'll use the product rule here. Y prime equals x times the derivative of e to the negative 2x plus e to the negative 2x times the derivative of x. So that's x times e to the negative 2x times negative 2 plus e to the negative 2x times 1. So we get e to the negative 2x times 1 minus 2x. Differentiate the function g of t equals e to the t over e to the t plus e to the negative t. We will use the quotient rule here. This gives us g prime of t is equal to e to the t plus e to the negative t times the derivative of e to the t minus e to the t times the derivative of e to the t plus e to the negative t divided by e to the t plus e to the negative t squared. Sorry about that. I messed up there a little bit. And that's equal to e to the t plus e to the negative t times e to the t minus e to the t times e to the t minus e to the negative t all over e to the t plus e to the negative t squared. When we multiply out the numerator, we get e to the 2t plus 1 minus e to the 2t plus 1 all over e to the t plus e to the negative t all squared, which is equal to 2, not t, 2, over e to the t plus e to the negative t squared. A practical application of the exponential function uses the form q of t equals q naught times e to the kt, where q naught and k are positive constants and t is greater than or equal to 0. A quantity q of t growing according to a certain law experiences exponential growth. Show that for such a quantity, the rate of growth of the quantity q prime of t at any time t is directly proportional to the amount of the quantity present. Well, q prime of t is equal to q naught e to the kt times the derivative of kt, which is equal to q naught times e to the kt times k, which is equal to q naught e to the kt, which is k times q of t. Since k is a positive constant, k times q of t is a constant multiple of q of t, and thus q prime of t is directly proportional to q of t for any value of t. Find the inflection points of the function f of x equals e to the negative x squared. The first derivative of f is f prime of x equals negative 2x e to the negative x squared. The second derivative is f double prime of x equals 2e to the negative 2x times 2x squared minus 1. If f double prime of x equals 0, then 2e to the negative x squared times 2x squared minus 1 equals 0. 2e to the negative x squared is never equal to 0. So x equals plus or minus 1 over the square root of 2 are the only candidates for inflection points of f. Those are solutions to 2e to the negative x squared times 2x squared minus 1 equals 0. If we check the signs of f double prime, we find it is positive for values that less than negative 1 over the square root of 2, negative between negative 1 over the square root of 2 and 1 over the square root of 2, and positive for values greater than 1 over the square root of 2. So there are inflection points at both values. Then, since f of negative 1 over the square root of 2 is equal to f of 1 over the square root of 2 is equal to e to the negative 1/2, the inflection points of f are negative 1 over the square root of 2 e to the negative 1/2 and 1 over the square root of 2 e to the negative 1/2.